Now let's talk about the expansion of the universe and of space-time itself. It started with observation, this observation, of a particular galaxy which, if it were nearby or not moving, has emission lines and absorption lines at particular wavelengths, which indicate the chemical elements that it's made of. But in the lower example, we see a distant galaxy. The spectrum is familiar and similar in that the same spectral features are there. This galaxy is made of the same ingredients chemically, but the entire spectrum is shifted by 5% to the red, to longer wavelengths. This redshift is an indication that the galaxy is moving away from us at 5% of the speed of light. This was the fundamental type of data that was used to discover that we live in an expanding universe. It was another piece of work by Edwin Hubble. He started gathering redshifts, or spectra, for galaxies, and he noticed that almost all of them were moving away from the Milky Way, in the sense that almost all of them had spectra that were redshifted. So on the lower right, we can see spectral features of a particular element, in this case hydrogen, in absorption. And at the bottom, we see the laboratory reference frame, which is their unmoving wavelength, zero velocity. We can also see that that same element, hydrogen, in a nearby star is also barely moving, because the motion of the star compared to the Earth is very small compared to the speed of light. But as we move out to more distant galaxies, a nearby galaxy, then a distant one, and then a very distant one, the lines start to be shifted by a substantial fraction of their wavelength. And that shift indicates a high recession velocity. They're moving away from us. The correlation that Hubble measured is on the lower left. That was his initial diagram from 1929. And it shows a linear relation between distance, measured in parsecs, and recession velocity, speed moving away from us. So, a remarkable result. First, that almost all galaxies are moving away from the Milky Way, almost without exception. And the further away they are, the faster they're moving away from us. The best interpretation of this data is that the universe is expanding. And the slope of the line in Hubble's original diagram is given the designation in astronomy h0, Hubble constant, gives us the rate of the expansion. Now, redshifts were actually first measured by Vesto Slipher. As we've seen, Hubble in his major discoveries depended on other people's work. And Vesto Slipher not only measured redshifts before Hubble did, but he also commented on the relationship between redshift and distance. But Hubble did more and better work, and in the end he essentially got the lion's share of the credit. Hubble was quite careful in how he wrote about his data. And he actually never talked about the expanding universe, or an expanding universe at all. He was a pure observer, and so he preferred to talk about recession velocity, which is what he observed. This is the quality of Hubble that's very important. As an observational astronomer, he was careful not to make unnecessary inference. He just talked about recession velocity. These objects were moving away from the Milky Way with this speed, what he observed. He was similarly cautious with his declaration that the galaxies were external to the Milky Way. He put an important caveat in his paper about using Cepheid variables by saying that his result, this foundational result that galaxies were remote from the Milky Way, depended on what he called the uniformity of physics, the fact that Cepheid variables in a distant location in space operated physically the same way as Cepheid variables in the Milky Way, which is how the relationship was calibrated. He recognized that that was an assumption, that physics operated the same in different parts of the universe, and only if that were true could he use Cepheids to measure the distance to Andromeda. Just a very important distinction, and his caution is actually well justified in science, because we often don't know the answer. We're working at the limit of the data. Now, although Hubble didn't talk about expansion, meanwhile, there were physicists, including Einstein, who were using general relativity and recognizing that solutions to general relativity for a universe were never static, but always expanding or contracting. Einstein did some of this work, but actually the major result came from Alexander Friedmann, who did the important calculations to recognize that general relativity could describe the universe, and it would describe a dynamic universe, expanding or contracting. Well, Hubble saw recession, and so the obvious solution was the one of an expanding universe. Now in this diagram we can also see that Hubble's initial work is actually represented by the tiny blue box in the lower left. That was the original diagram that we just saw. And in this diagram, with data taken up to half a century later, we see that Hubble's original linear relationship between distance and velocity has been extended by factors of hundreds or thousands to distances of over 1 billion light years. So it's an extraordinary and central result in astronomy, the Hubble Law. Here's what linear expansion actually looks like in a two-dimensional analog. We'll mark out 2 or 3 galaxies here and see what happens over time. As the animation starts, these are the separations of these 3 galaxies from each other. As space expands in 2 dimensions linearly, the distance between the red and the green galaxy doubles, and the distance between the red and the blue galaxy doubles too. In other words, the nearby galaxy to the red galaxy is moving away from the blue one twice as fast as the other galaxy. So that is the Hubble Law. The most important thing to realize in this animation is that it doesn't really matter what your reference frame is. We could imagine that we are on the red galaxy, measuring the green one and the blue one, and those 2 data points would be part of a Hubble Law correlation. But suppose we lived on the green galaxy or the blue galaxy. I think you can see that we would see the same thing. Each galaxy in this animation is moving away from all other galaxies. And so logically, no galaxy can say, I'm at the center and I'm not moving. Every galaxy moves away from every other galaxy, and they see the same thing, a linear expansion, and each galaxy, or each observer on each galaxy, would see a Hubble Law. We can also use an analogy of a curved universe, the two-dimensional balloon analogy. And now imagine the galaxies were actually coins or beads glued to the surface of the balloon. That's important to do because galaxies do not expand as the universe expands. They are held together by their own gravity. But if you have beads or coins glued to a balloon and you blow the balloon up, you'd see the Hubble Law in 2 dimensions on a curved surface of a balloon. The distance between each of the coins or beads would get larger from the other ones, and if you plotted the relationship between how distance increased with time against all the other galaxies against each other, you get a Hubble Law in 2 dimensions. Interestingly, if you painted a wave on the surface of the balloon and blew the balloon up, you'd see the wavelength of the balloon increase. That's the redshift. So even though this is a little toy model of a curved surface of a balloon, the analog of light is quite accurate because that's what's happening. As space-time expands, which is the general relativity explanation for what Hubble saw, waves of light that travel through that space are being stretched by expanding space-time, and their wavelength is lengthening, and that is what the redshift actually is. Now that's a very important distinction, so let's look at it again. If you inflate a balloon and have expanding space, then in this case little ants on the surface will see all the other ants moving away from them, and the more distant ants move away faster, and that's what Hubble saw with galaxies. And every ant will see the same thing. No ant is at the center of this situation. They're all equally statist on the surface of the balloon. But look at the distinction here between that and the diagram on the top, where the balloon is expanding within a fixed space. Now there, the ants, or dots on the balloon, are moving with respect to a fixed framework. That's what a Doppler shift would be, because in Doppler shift we have a reference frame for measuring motions, for measuring speeds of things, like moving cars or moving planets within the solar system. But in cosmology the situation is different. It's the space-time itself, the grid itself, that is expanding. It's invisible space-time, of course. The galaxies are just markers of space-time. But if there were an external space, then we'd have something like the Doppler shift or the Doppler effect. But what we have is not the Doppler effect. It's cosmological redshift because the space-time is expanding. And so these are the conclusions we draw from this situation. And we also give on the right a 3-dimensional analogy, kind of a little bit better than a balloon, the expanding raisin loaf model. So put raisin bread in the oven, and as it cooks in 3 dimensions now rather than 2, all the raisins move away from all the other raisins in 3 dimensions. and they would get a little three-dimensional raisin Hubble Law. Now the analogy falls apart because, of course, the raisin bread has an edge, so you can't do this past the edge of the raisin bread. But it at least extends the balloon analogy and makes it clear you don't have to do it on a curved surface. So what we conclude from this work is that the redshift is not the Doppler effect. It's caused by the expansion of space, and that's got a particular term for it, the cosmological redshift, and it's explained in general relativity. We see galaxies moving away from each other, and since every galaxy sees the same thing, there's no center to the expansion. There's no reason to claim one, and there's no way to claim one. The cosmic expansion is the unfolding of all space and time since the Big Bang, and that means there actually doesn't have to be an edge too, which is a little hard to imagine. Finally, we're limited in our view of the universe and space by the time it takes distant light to reach us. And that means the universe we live in has an edge in time, but it might not have an edge in space. And in fact, astronomers have not detected an edge to the universe so far. And that's the end of this topic.